Alright, so we've been talking about this Weierstrass's excess function, and unfortunately we couldn't complete the derivation the other day, so we'll have to actually start from again scratch, because I can't just invoke those results and say that, oh, carry on from here, neither do I remember all of that. So, but we can work it out, but we'll do it pretty quickly. Before that, I just like to clarify there was a small little error, not that we are going to be using it, but nonetheless I would wish to clarify that error. So yesterday when we drew this figure, and I think some of you are a little confused, I didn't really completely understand your objections or your questions about this, but then I thought about it and I realized where the mistake was. So the idea was right, but the mistake was this. So we had this point x bar over here, and then we had this point x bar plus epsilon, and then we had this point d, right? And we said that here is where the perturbation is. So in this segment it was just a straight line, and in the next segment the perturbed curve was just the original curve plus a linear term, and in the expression for the linear term it turns out I had sort of messed up a bit, and the reason being the following. So once again, the coordinate of this point, if you see, the slope of this line was w, right? So the coordinates of this point would be x bar plus epsilon comma y at x bar plus epsilon w, isn't it? This was right, yeah. And at this point, of course, it is just y at d, which is the y coordinate, and d is the x coordinate, right? Now what we were trying to do was we were trying to characterize this linear term here. So in the third phase, if you recall, for x bar plus epsilon to d, yeah, we said that y x comma epsilon should be equal to y of x plus some perturbation, and in characterizing that perturbation is where I had actually made the mistake. The idea was still correct, but the slope and everything I miscalculated. So the reason why I am clarifying this is, if you look through the book, it appears like the expression pops up suddenly, but it's important to understand what the idea behind it is, so you'll never forget this, you'll not even feel the need to remember this, you can work it out. See, at this point, what part is the perturbation contributing? It is this, right? And that is not exactly this, that is exactly the difference between this and the value at this. And this point is what exactly? This part is y evaluated at x bar plus epsilon. So the overall contribution of the perturbation is the difference between this and this. That's what the linear term is contributing at this point, the linear perturbation. At this point, what is the perturbation contributing? Since it has merged with the original curve, it's contributing exactly 0. So if I were to characterize the perturbation term only, which gets added to this, it attains a value yx bar plus epsilon w minus y evaluated at x bar plus epsilon, and at this point it attains a value 0. So by this reasoning, once again now calculate the slope. This is where I think I had erred, because I had written y of d, which is what raised a few eyebrows. I missed it then, but better late than never. So what's the difference then? You see, look at this, the slope is y x bar plus epsilon w minus y x bar plus epsilon. That's the overall value here, yes, minus 0 divided by, what's the difference between the x coordinates? X plus epsilon minus this, right? Yeah, this is d. So, x plus epsilon, or rather x bar plus epsilon, I am sorry, minus d. So, that is the slope, is not it? What else do we know about this? That it must vanish at x equal to d. So, you just get this going and that is your expression. So, you get rid of the 0 and you will see that now the expression is perfect, it makes sense. So, I think instead of this term here I had somehow mistakenly put y of d, not that it matters. You will see in our derivation subsequently this will not matter at all, but I just wanted to set the record straight because now this is correct. Okay, so this is for x belonging to the interval between x bar plus epsilon to d. Okay, so that is the correction. Please incorporate that correction and I hope you also understand why it is coming. Yeah, the reasoning is exactly the same. You have to calculate the slope, but the calculation I had somehow messed up. Alright, so I just wanted to get that out of the way. Is this clear to everybody? This clarification is okay? Alright, great. Now let us get back to the business of evaluating that nasty derivative and picking out terms from there to see what our condition should boil down to. Condition for a strong minima here that we are trying to arrive at. Strong why? Because this kind of a perturbation is not close to the original curve in the sense of the 1 norm, but rather in the sense of the 0 norm. Yeah, okay. So now this is what we were after, right? So this means we are essentially only going to look at this interval between x bar to d, because that is the only place where it differs from j, the original j for the unperturbed curve. Okay, so we are going to split it up into, as before, x bar to x bar plus epsilon, and then the Lagrangian x, y, x comma epsilon, and y prime x comma epsilon. Now on occasions, as I said yesterday also, I will be replacing this y prime with y subscript x. You should read the two as same, at least in this context. Okay, plus dd epsilon from x bar plus epsilon to d. It's again the same thing, x, the perturbed curve, that is y x epsilon, and y prime x epsilon dx. Okay, so I'll collect together terms like I was doing yesterday. What's this going to lead to quickly? As we pointed out yesterday, you see in this portion, what does this turn out to be? Y at x bar plus w times x minus x bar, right? Is there any dependency on epsilon? No, none whatsoever. This term gets replaced with w, right? So no dependency of the integrand on the epsilon term here, and hence applying Leibniz rule, the only place where the epsilon dependency shows up is in the upper limit of the integral. So what should we do? What's the term we pick up from here? Differentiate this with respect to epsilon, that gives 1, and substitute x bar plus epsilon wherever there is x. Yes. So we have L x bar plus epsilon, y evaluated at x bar plus epsilon comma epsilon, and y prime evaluated at x bar plus epsilon comma epsilon, right? Plus, so we'll collect together this term and hereafter only consider or bother ourselves with only this term, the evaluation of this term. So let's collect this term here as term number 1. So it's L x bar plus epsilon y x bar plus epsilon comma epsilon y prime x bar plus epsilon comma epsilon. Great. What about this? Of course, once again you see the upper limit is not a function of epsilon. So when you differentiate d with respect to epsilon, you get 0. The lower limit differentiated with respect to epsilon gives 1, but because it gets subtracted, so there will be a minus 1. Upper limit minus lower limit in Leibniz rule, so minus. So you straight away write minus L. What about this? X bar plus epsilon y x bar plus epsilon, sorry, comma epsilon, and y prime x bar plus epsilon comma epsilon. But there's more to it, right? Now whatever's inside here, we know, in fact we had just written it a while back, the correct expression, not that I'll be using it by the way, yeah. So don't get me wrong, I'm not correcting that because I'm going to be actually explicitly differentiating that with respect to epsilon, okay. But in this particular domain, you see, now there is a dependency on epsilon in y and y prime as well. So we have to be careful of this, right? By the way, here, if you look at this, what can I replace this with? W, right? So let's do that right up front. Just to make this simpler. What about this? Sorry? Yes, W epsilon, because now you have covered the entire distance, right? But that's okay. We'll just make a mental. The main thing is that this gets replaced by W. That is going to be the crucial detail in our derivation. Anyway, now then, there is still this term to be handled. Remember, we've just done one of the differentiations under Leibniz rule. Now what happens? Plus, now this fellow inside the integrand gets differentiated with respect to epsilon. Where all are the epsilon dependencies appearing? Here as well as here. In what form? In what manner? Like how do we handle this? We are not going to explicitly differentiate as I said. So we are going to just denote it by its differentiation with respect to epsilon. Okay, we will use the subscript. So when we differentiate L with respect to this, the partial of L with respect to y by the chain rule multiplied by y epsilon. And then when we concern ourselves with this term, we will have the partial of L with respect to y prime times y. There's a double subscript now because this y prime is basically y subscript x. So we'll have y subscript x epsilon or epsilon x. The order doesn't matter in this case. Yes, so that's what we're going to do. Let's do that. So we'll write this integration as x bar plus epsilon to d L y x y x epsilon y prime x epsilon times y subscript epsilon. Plus what else? Anything else? multiplied by y dash, but I'm going to replace that dash for simplicity of notation. So, epsilon x, x epsilon, epsilon x, the order won't matter. So, this is x comma epsilon dx. Okay. Let us stitch these fellows together and keep them in our box here. Okay. Let's do that. So, we have these two terms, we set them aside, and hereafter we shall only bother ourselves with this term. So, we have integration Ly between x bar plus epsilon to d x y x comma epsilon y prime x comma epsilon times y epsilon x comma epsilon dx minus L x bar plus epsilon. Of course, you could jolly well replace this with the same thing that you have replaced this fellow here. Doesn't really matter. You understand this, right? You know exactly what the value is at this point, but it's not going to be of much consequence. I've written this here just as a recollection of sorts. I might have also written this as, you know, y evaluated at x bar plus epsilon comma epsilon. Doesn't matter. Either way it would have been okay. The main thing, as I said, was to replace this with w. Okay. Anyway, so let's x bar plus epsilon comma epsilon comma y prime x bar plus epsilon comma epsilon okay. That's the blue box part. So now I'm not going to act on these fellows further. Whatever I'm putting in this box here, I'm going to keep them like this for now. So I'm going to only bother with whatever's left now. So I won't write equal to here. Let me just turn my attention to this surviving term here. So what do you think is it that we are going to do here with this term? Our favorite tool again, insofar as the integration goes, integration by parts. So this part we are going to call as u, this part we are going to call as dv. So now let us carve out a space for us here and see what that term leads to. So that's going to be L y prime x y x comma epsilon y prime x comma epsilon, and integration of this with respect to x means this subscript x goes off. So you'll be left with just y epsilon, the partial of y with respect to epsilon here. So y epsilon x comma epsilon. But you'll need to set those limits, right? The limits of the integrations. X bar plus epsilon to d. Okay? The first term, so u dv integration is uv minus integration v du. What's v du? Minus, what is v? This du. So ddx of this whole thing, right? So integration x bar plus epsilon to d ddx of L y prime x y x comma epsilon y prime x comma epsilon times y epsilon x comma epsilon dx. Yes? Let's pull out this term now and put it in our bag. Okay? You have to just keep tab that you're not missing any term at any stage. So to be just a little mindful. Other than that, it's just integration by parts. Nothing else, no fancy observation or nothing very smart about these steps so far. You just have to be a little careful. Good amount of bookkeeping should do it. So what's this term? Minus integration x bar plus epsilon to d, sorry. This color is visible, I hope, right at the back. Okay. So now having done all of this, I can actually erase all these box terms. So what am I left with? In this overall term now, everything is here as term 1, term 2 and term 3 except this. Let's try and make some observations about this if we can. So our sole focus should now be turned towards unraveling whatever's there lurking within this term. Any doubts about any of these steps so far? So clear, right? Great. If you evaluate this at d, if you pass the argument of x as d here, what happens to this? What is, for example, y d epsilon equal to? Sorry? It is just same as the unperturbed curve y of d. Right? Is there any epsilon dependency on this? No, right? So when you take this partial of this with respect to epsilon as akin to taking a differentiation of this with respect to epsilon, which is equal to 0. So in fact, this term vanishes when you substitute x is equal to d. Agreed? So all you will be left, is this clear? Because y at d has no dependency on epsilon. Whatever business has gone on behind the back prior to d has evaporated by the time you have reached d. There is no further dependency. No matter what epsilon you had chosen or you had chosen, you eventually converge upon this same point at d. So it has no relation to whatever your choice of epsilon was. Therefore, the partial with respect to epsilon at that point is 0. So this in fact just boils down to minus L y prime x bar plus epsilon y x bar plus epsilon comma epsilon and y epsilon, sorry, multiplied by, right? Oh, okay, I've missed this, right? Y prime x bar plus epsilon epsilon. It's a huge term, so I'll have to be mindful. So it's y epsilon x bar plus epsilon comma epsilon. That's all that remains. Apart from whatever's boxed here, this is all that survives of this term, right? What can you say about this term now? What is this term? What does this evaluate to? You already know what this evaluates to, don't you? It is this. It is this sitting right in front of you. So y at x bar plus epsilon comma epsilon is equal to y evaluated at x bar plus epsilon w. Okay, we are very close, except that there is one observation, a subtle observation that you need to make. Now, if you take the derivative of this with respect to epsilon, the right hand side is very obvious, it's just w. What about the left hand side? They're all tangled up. It's not as if epsilon is appearing only as a second argument here. So, when you take the derivative of this with respect to epsilon, you have to first consider the dependency of the first argument with respect to epsilon. So, you have to differentiate with respect to the first argument, which is tantamount to taking the derivative with respect to x and substituting back whatever is there. And when you take the derivative with respect to second argument, that's just y subscript epsilon. Do you follow this? This is the most crucial observation here. Is this clear? Because epsilon is tangled up in both of these. It's not like you take epsilon here and you just take the derivative with respect to the second argument here. The first argument also involves epsilon, just exactly in the same manner as it involves x. Wherever there was linear term in x, there will be linear term in epsilon. Wherever there is a trigonometric term in x, there will be a trigonometric term in epsilon, and so on and so forth. Right? So, if you now take dd epsilon of this, what happens? You have to account for the partial with respect to this first argument times the derivative of x bar plus epsilon with respect to epsilon, which is 1, and the partial of this with respect to epsilon times the derivative of epsilon with respect to epsilon, which is again 1. So, what does this lead to? Tell me, what is it? What great discovery have we made through all of this? Look, the right hand side is immediately very straightforward, it's just w. So, if you differentiate both sides with respect to epsilon, the right hand side turns out to be w. What about the left hand side? So, you have yx, but then yx we are more familiar with y prime as yx, yeah. So, we can just say y prime x comma epsilon. Okay, you can just say x bar plus epsilon comma epsilon plus y. See, I am playing on and off with this prime and this subscript x, yeah. Please allow me that abuse of notation, otherwise things get really messy. This prime is essentially derivative with respect to x. Sometimes I write x as a subscript, sometimes I decide not to. Loosely speaking, it's important to understand what's going on here. That's what this is, right? What we need here is, sorry, where were we? Yeah, what we need here is this, a handle on this object, and we already have a handle on that object through this, don't we? How so? I hope I can erase this right hand side part. You're all through with this, I hope, right? Okay, let me clear up some space here. So, what this yellow part tells me here is that y epsilon x bar plus epsilon comma epsilon is equal to w minus y prime x bar plus epsilon comma epsilon. In view of this term now becomes what? Let's call that the fourth term now. First term, second term, third term. This was the only term surviving in this derivative. So, let's look at the fourth term now. So, what's the fourth term now? We have to just substitute this, right, here. So, we have minus L y prime x bar plus epsilon y at x bar plus epsilon comma epsilon and y prime at x bar plus epsilon comma epsilon times w minus y prime at x bar plus epsilon comma epsilon. Is that clear? So if you sum together term 1, term 2, term 3 and term 4, we actually have this entire term. Agreed? We haven't missed anything. Correct? Let me erase everything apart from those 4 terms over there. Our claim is that for epsilon is equal to 0, we have a strong minima, because that's the nominal curve we started with. Correct? What happens, I wonder, if we just plug in now epsilon as 0 plus? What happens to this 1 plus 2 plus 3 plus 4 as epsilon tends to 0 plus? Yes, first term first, L at x bar, y at x bar, comma, w. That's it, first term taken care of. Second term, well, I'll look at this second term here. The only terms that contain integrals are the second and the third term. If I merge together the integrals from the second and the third term together, do you see something familiar? We are looking for, yes, it's an Euler-Lagrange equation sitting over there. It's a strong extrema that we are looking for. Now, any necessary condition for a weak extrema must also needs be a necessary condition for a strong extrema. So, if indeed as epsilon tends to 0 plus we do land up with a strong extrema, it must satisfy the Euler-Lagrange condition. So, therefore, the sum of this term over here and this term together, they will give us the Euler-Lagrange equation, which means that they simply vanish. Is that clear? It's important to understand the arguments. Once you follow the arguments, everything else is almost crystal clear. Okay, what about this? This is the term that survives. If you substitute epsilon is equal to 0 plus, it means you are back to the original curve again. Yeah, so whether you write as x bar comma 0 or just x bar, it matters not. You are talking about the nominal curve with epsilon set to 0, you are back to the nominal curve, there is no perturbation whatsoever. Yeah, so what is this? Minus L evaluated at x bar, y evaluated at x bar, comma, y prime evaluated at x bar. Is there anything surviving from the left hand side here from terms 1, 2 and 3? Nothing. The only term that remains is term 4 over here. Again you substitute epsilon at limit tending to 0 plus from the right hand side. What happens? Minus w minus y prime x bar, right, times L y prime x bar y at x bar y prime at x bar. Yes. So this is the differentiation of J with respect to epsilon. What does it result in? What have we just defined this as? Go back to the excess function, the E function that we have just defined yesterday. What does it turn out to be? is this not the excess function evaluated at x bar, which is a non-corner point? X bar. What else? Yeah, so there is also y at x bar. Then there is y prime, right? Y prime at x bar, comma, w. And look, this w was arbitrary, wasn't it? W was arbitrary for any possible real value of w. What does this need to be? This needs to be greater or equal to 0 for this to be a minima. This fellow needs to be greater than or equal to 0, right? So in fact, we arrive at the condition that Weierstrass did in the 1860s through all of this work, that in fact the Weierstrass's excess function, with the third argument being the slope at a non-corner point. Okay, what was the criteria on x bar? It was a non-corner point. So at any non-corner point, you choose any arbitrary w, real value w, yeah, and if you pass on the argument y prime here, then it must necessarily be non-negative. So we have a condition from Weierstrass-Erdmann for what happens at corner points. Some continuity requirements are necessary for broken extremals at corner points, and at non-corner points for strong extremals we have this. So instantly we have departed from this calculus of variation setting with weak extremals, and now we are looking at conditions for strong extremals here, which says that this Weierstrass's excess function had better be non-negative at this point, at a non-corner point, okay.